This resource is the fourth in a 6-part series on exponents and logarithms. Part 1 defines exponents and logarithms. The exponent laws are defined, and justification for the exponent law of multiplication is provided. We consider how to transform between exponent notation and logarithmic notation, and define two special bases for logarithms. Part 2 explores expanding and contracting logarithms. Multiple examples of each are provided. Part 3 demonstrates solving logarithmic equations, with examples provided. Part 4 considers solving exponential equations. A general solution method is provided, and examples are given. Part 5 delves into solving exponential growth equations, with examples. Part 6 looks at solving exponential decay equations, with special emphasis on half-life problems. In the last resource, we considered logarithmic equations. One of the methods for solving logarithmic equations involved transforming the logarithm into an equivalent exponential form. In those exponential equations, the variable term never became the actual exponent. It was always on the opposite side of the equal sign. How could we solve an equation where the unknown was actually in the exponent, which are exponential equations? There are two possibilities for exponential equations. Either both sides of the equation can be expressed as powers of the same base, or they cannot. The method we use to solve the equation depends on the format of the equation. First, we will consider the case where both sides of the equation can be expressed as powers of the same base. We will begin by writing the equation as those powers of the same base. Next, we do a hidden step. We take the common base logarithm of both sides of the equation. For example, if both sides of the equation could be expressed as powers of 2, the hidden step would be to take the base 2 logarithm of both sides. This results in setting the exponents from both sides of the equation equal to each other. We finish by solving this equation. Let's look at an example. Suppose we have the exponential equation 3 raised to the power 2x minus 7 equals 243. First, we want to rewrite the equation so that both sides are expressed as powers of 3. 243 equals 3 raised to the 5th power. So we have 3 raised to the power 2x minus 7 equals 3 to the 5th power. By taking the base 3 logarithm of both sides of the equation, we are able to set the two exponents equal to each other. So we have 2x minus 7 equals 5. Adding 7 to both sides, we are left with 2x equals 12. Dividing by 2, we find that x equals 6. The same base method is nice, but it only works for those very special cases. The method we will now consider, where the two sides of the equation are powers of different bases, is the generic case. It works for any exponential equation, even for those where both sides of the equation can be expressed as powers of the same base. First, we ensure that the exponential term is isolated. Next, we take the natural logarithm of both sides of the equation. While we could use any logarithm, certain real-world problems actually use base e, so it is easier to get in the habit of using the natural logarithm for solving. Simplify the expressions. Because we are taking the logarithm of a base to a power, the logarithm laws allow the exponent to become a coefficient of a logarithm term. Then solve the equation. Let's look at a couple of examples. Let's start relatively simple. Suppose we want to find to which power we raise 5 to get 134. Because the exponential term is isolated, we take the natural logarithm of both sides. Using the logarithm rules, the natural logarithm of 5 raised to the x power becomes x multiplied by the natural logarithm of 5. While we could find the natural logarithms of 5 and 134, those numbers are irrational decimals. We want to remain exact in our calculations as long as possible and only have to round values one time. So we will leave our expressions in terms of the natural logarithms. To solve for x, we would divide both sides by the natural logarithm of 5. The exact answer would be x equals the natural logarithm of 134 divided by the natural logarithm of 5. Using a scientific calculator, we find that this amount is 3.043 when rounded to 3 decimal places. Now let's look at a more involved example. Suppose we have the equation 7 times e raised to the 2x power minus 5 equals 58. First, we have to isolate the exponential term, so we add 5 to both sides of the equation. This leaves us 7 times e raised to the 2x power equals 63. We want to have the exponential all by itself, so we divide both sides of the equation by 7. We now have e raised to the 2x power equals 9. Now we take the natural logarithm of each side. Recall that e to a power and the natural logarithm are inverse functions. Therefore, the e and the natural log cancel each other out. We are left with 2x equals the natural logarithm of 9. To solve, we divide both sides by 2. Our exact answer would be x equals the natural logarithm of 9 divided by 2. So our value is approximately 1.099. Exponential equations solve for an unknown value in the exponent. Sometimes each side of the equation can be expressed as a power of the same base, in which case we only need to set the exponents equal to each other and solve. A more generic solution method involves isolating the exponential term, taking the natural logarithm, simplifying, and solving from there. Why do we want to solve exponential equations? Many real-world phenomena can be modeled using exponential equations. We will explore these situations in the next installment of the exponential and logarithm series.